Hey Algebra 2, here's your lesson on 9.5 with natural logarithms. Now I personally think natural logarithms can be a little bit confusing, mainly because we start off with this new idea called e. E can be thought of a lot of ways. Some people call it an irrational constant. Some people think of it like the number pi, where it's related to such an idea where we're writing a number as a letter, and that can be a little bit confusing. So let's think about it this way. If we invest $1 at 100% interest for 1 year, we will keep increasing the compounding and see what happens. So we've created a little bit of a table here, and from this table, we start to see the equation given here. Now, if you haven't seen this equation before, I'll go over it real quick. A is the amount at the end of the period. P is the principal, or the original amount that you put into the account. R is the rate at which something is compounding. N is the number of times per year that something compounds, so number of times. And then T is the time, and we always talk about it in terms of years. So if we ever talk about it in months, we need to find a way to rewrite that in terms of years. So when we make this table, you'll see that compounding something annually at 100% interest gives us $2. Semi-annually, it's about $2.25, and so on and so forth, all the way down to this idea that if we compounded it 1 million times, we would still only have about $2.72. So if we continuously compound something, the value that we get is the number e that I started talking about. And if we find it on our calculator, mine is right above my ln button. If I hit second ln, it's going to give me e, and I just want the most basic form of it, so e to the 1. When I punch that in, I see that that number that it's talking about is about 2.718 ... So e is an irrational number, just like the number pi that I was telling you about. So a quick little review, the common logarithm has a 10 for a base. We work with log base 10 of whatever number we want to put in our parentheses. Something called a natural logarithm has e for a base, so log base e of whatever you want to put in. However, you're very rarely going to see a natural logarithm written like this. More often than not, you're going to see it written as ln, so the natural log ln. So based on our wisdom of logarithms, we want to evaluate the following. So ln of 1 is the same thing as log of e to the 1. Now we can auto put that in our calculator, or we can just work with a little bit. I'm going to put it in a calculator just to show you what it pops out as. ln of 1 is 0. And why is that? Well, if we go from logarithmic to exponential, e raised to the x equals 1 is one of those forms that we're really, really comfortable with at this point, because the only way to get a 1 from any number is to raise that number to the 0. ln of e is a little bit more complicated. ln of e is very, very similar to writing log base e of e. And if you remember from our previous units, whenever the base matches what's inside the parentheses, our answer is just 1. And that holds for natural log of e. Now, we go even further when we raise e to a natural log. But the cool thing about this is e and ln kind of cancel each other out. So let's see what happens when we write this. Log base e of some number x is equal to the natural log of 7. So log base e of what equals log base e of 7? Log base e of what equals log base e of 7? Well, if we're familiar with our log properties, we remember that when they have the same base, whatever is in their parentheses must be equal. Excuse me. So in this case, we know that x must equal 7. And just like I said before, e and ln, since they're opposites, cancel out. So the e cancels out the ln cancels out the e, and we're just left with 7. The same thing can be said for taking the natural log of e. The same way that raising e to the natural log, taking the natural log of e cancels it out the same way. But let's just familiarize ourselves with our properties. Remember, if something is a power inside the parentheses, it becomes a multiplier out in front, and we're left with just the ln of e. But we know ln of e can still be written as log base e of e, which is just 1. So if we're trying to figure out what that's equal to, it's just 1 times the multiplier of 4x plus 3. And our final answer is just 4x plus 3. These cancel each other out, just as they did in this problem. But there's not always going to be these nice changes that we can make. Sometimes we're just going to have to put it into our calculator to evaluate it. And it's really nice because all the scientific calculators should have ln. When I put in ln of 5, I get 1.61. I'm gonna round this to 2 just because I don't want to deal with the, well, nope, I'm gonna round it to 4, I lied. 6094. I do prefer 4 decimals. I like to round it nicely if I can to that second decimal, but not this time. The next one's a little hard to see because of printing errors, obviously. You know how I am with that. But e raised to the 42 in our calculator, 4.2. I'm just going to rewrite this. I'm sorry for the poor printing. E to the 4.2 gives us a value of 66.6863. Again, something we just have to put in a calculator. The last one is even worse. I'm sorry for that. It's e to the negative 1.2. And again, I have no way to evaluate that with the methods I was using up here, so I just have to put it into my calculator as e raised to the negative 1.2. That ends up being 0.3012. So this is a little tricky. Natural logs and e can be really challenging, but my biggest takeaway, at least from this first page, is you remember that ln and e cancel each other out. They're opposites of each other. The same way that a square cancels out a square root and a square root cancels out a square. If you have ln of e, they cancel. If you have e raised to ln, they cancel. And whatever is left, whatever else is happening, becomes your answer. All right, let's keep going with this. Let's flip over to the back side here. So, good news. Equations and inequalities involving base e are easier to solve using natural logarithms than common logarithms. So all of the properties of logarithms that we've learned apply to natural logs as well, which is really, really exciting. So let's solve some of these. Well, if we're trying to get x alone, we should probably move everything away from x as much as we possibly can anyway. For me, this starts by just moving the 7 over. I get 5e to the negative x equals 9. The next thing I want to do is divide by that 5, obviously, so I have e to the negative x equals 9 over 5. And now, in order to get rid of that e that's bothering me, I'm going to take the natural log of both sides, and I'm just going to indicate that with an ln out in front. So when I take the natural log of e to the negative x and the natural log of 9 over 5, remember what I said on the last page. Those end up canceling out. And how do they do that? Well, technically I have to take this exponent and make it a multiplier. So negative x becomes the number in front, and I have ln of e, still set equal to ln of 9 over 5. And then, of course, this becomes just the 1. So I have negative x equals ln of 9 over 5. Divide both sides by that negative, throw it into a calculator. This one, I don't want to finish my parentheses. I want to put it all in as 1. So ln of 9 over 5 divided by negative 1 is going to equal negative 0.5878. Negative 5.878. Again, just a little algebra skill with that natural log thrown in. All right, if you're watching the video and you haven't already seen this, I would like you to try this next example on your own. So pause the video, give it a shot, and then come on back. All right, hopefully you paused the video. Hopefully you were successful. However, if you're not, we're going to walk through it together. So no worries. I'm going to move that 2 over to start off. Again, all I'm trying to do is get x by itself. So I get 3 times e to the x equals 2. Divide both sides by 3. I get e to the x equals 2/3. The only way to get rid of an e is to take the natural log of it. So I take the natural log of both sides. When I do this, my power becomes a multiplier, and I get x times ln of e equals ln of 2 over 3. This becomes that 1, and x equals ln of 2 over 3. When I throw that into my calculator, I get negative 405.5. Again, the only new thing that we've introduced today is how to cancel out that e. All right, it's time for some word problems. So suppose you deposit $1,000 in an account paying 2.5% annual interest compounded continuously. That's what we like to hear. When interest is compounded continuously, the amount A in an account after T years is found using this formula. Most of you have probably seen the PERT formula, but if you haven't, or you haven't in a while, it's a great refresher, where P is the amount of principal and R is the annual interest rate. So what is the balance after 10 years? Well, let's start setting up our knowns. I always like to write down what I know and take it out of the word problem format that can be so intimidating to some people. So our principal amount is that $1,000. So I'm going to write that down. I'm paying 2.5% interest. And when I put that in my problem, I know I'm going to write it as a decimal of 0.025. I'm compounding continuously, and it then says the balance after 10 years. So my time is going to be 10. From there, all I'm doing is plugging it into the formula. A equals P times e to the RT. My principal is $1,000. My E is that constant, and I'm raising it to the R times T, or the 0.025 times 10. I can go ahead right away and throw this in a calculator as long as I'm careful about it. 1,000 times E raised to the 0.025 times 10. And I get back a value of A equal to 1,284.03. And this one I do have to round appropriately because we don't use 4 decimals when we're talking about money. So please be aware of the situation you're working on there. All right, the next one asks, how long will it take for the balance in your account to reach at least $1,500? Well, this one uses very similar information, so I don't have to rewrite any of my knowns, but I do have to plug it in slightly differently. I want the amount in my account to reach at least $1,500. So when I say my amount, I don't say equal to, I want to say greater than or equal to. And then, of course, I still start with the same principle. I still have E. My rate hasn't changed. However, this time I have the amount and not the time. So I'm going to be solving for T in this case. How do I solve for t? Well, I just have to get it alone. So let's start moving things away. Let's start by dividing both sides by 1,000. I get 1.5 is less than or equal to e raised to the 0.025 times t. The only way to get rid of that e is to take the natural log of both sides. So natural log of 1.5 is less than or equal to the natural log of 0.025 to the t. Remember, my power becomes my multiplier. So when I rewrite this, I'm going to say 0.025t outside of ln of e. The left side stays the same. We love it when we see ln of e because we can just cross it out there. And then we're just working with numbers. Now we are only working with ln of 1.5 divided by 0.025. And we get that t is greater than or equal to 16 point, round to the 100th, 2 years. So I'm going to rewrite this just because I prefer my variable on my left. I'm going to say it's about 16.22 years. Once we get over the intimidating idea of these natural logs and this e, it's really nice because all we're doing is basic algebra skills. However, I totally understand how working with e and natural log can be a little bit overwhelming sometimes. So, last thing, an understanding of the natural logarithm can help us solve basic equations too. So if I ask you to solve for x in these, ln of 5x equals 4. Well, I remember that ln can also be written as log base e of whatever is in the parentheses. All I've done is rewrite it in a less common way. Now that I have a log with a base, I can rewrite something in logarithmic form into exponential form. And I can say that e to the 4th is equal to 5x. Once I know that, I can plug it into a calculator because I know e is just a number. So e to the 4th divided by 5 gets x alone, and x is approximately 10.9196. Let's see that again. That was pretty fast, so let's see if I can manage that just a little bit slower. I want to solve to get the ln by itself before I start off because I like to not have anything around my natural log when I'm working with it. So let's first move the 1 over. That becomes 4. And then I'm going to divide both sides by 2 just to get this 2 out of the picture. So I end up having ln of 3x equal to 2. And all I did there was get the natural log by itself. Once I'm here, I remind myself that this is the same thing as log base e of 3x equals 2. And that again, I can just rewrite it as e to the 2 equals 3x. And by dividing both sides by 3, I get x alone to equal 2.4630, approximately. All right, last one. If you can't solve it any other way, try rewriting it with that log base e. Log base e of x squared equals 9. I can rewrite this as e to the 9th equals x squared. And then, of course, if I take the square root of both sides, I get x is equal to plus or minus the square root of e to the 9th. Not a very pretty equation, not a very pretty answer, but when we plug it into our calculator, we're lucky enough to get plus or minus 90.0171. Don't be overwhelmed or intimidated by these big numbers. Again, they're just numbers. They don't have any context in this. However, I understand how they can be, so if you have any questions, please don't hesitate to let me know.